buckling, and so we're going to start off with the Euler equation. So Leonhard Euler studied under Bernoulli's brother and utilized some of Bernoulli's ideas to create a formula for the maximum capacity of a column. So he had some force that was pushing down, causes the column to bend or buckle. And this is the equation that found the maximum capacity. So you have pi squared times E, which is elasticity, times K, which is kind of like the spring constant, and then we have the unbraced length. The column formula was derived assuming that the stiffness moment at any point on the column is equal to E times K squared over rho, where E and K were constants to be determined through experimentation, and rho is the radius of curvature. Using E as a strength property and K as a dimensional property of the member, Euler was able to determine that E times K squared is equal to the force times the unbraced length cubed divided by 3 times the deflection. So using this, you can find what the deflection at the end of the cantilever would be. Alright, so the original column equation was actually derived assuming that you have a 10 at both ends, and that makes it to where the distance between the points of zero bending moment would be the full length. And so if you have different end conditions, then that's going to change what the distance between the points of zero bending moment are. So this is in the AIC manual, and you can either use theoretical K value or the recommended design K value. And normally we use the recommended value because it's impossible to make a column actually theoretical. And so, yeah, we can see that 0.5 here goes from here to here, and those are the points of zero bending moment. And then, yeah, all the other ones are based off of going from the length of zero bending moment to zero bending moment. Here's a picture of someone who actually put weights on and showed what the actual deflection or buckling of the column would be based on the different end conditions. And you can see at the top that it actually takes more weight to buckle different types of end conditions. Okay, so we have a couple examples here, and I just used the design references in the back of the AISC, and you can use those to solve for the buckling force. So this example is just for flexure buckling. Determine the column capacity for a W12 by 50 with A992 column with fixed ends and an unbraced length of 15 feet. So whenever you're actually designing, an easy way to check it is if you just make an actual Excel sheet. So we can just go through here and plug in our gross area.
Zoom it in a little bit. Control scroll.
So yeah, I just copied the E3 page, so that's all the equations you can use. But
that's good.
I have it where you can plug in your red values, and it takes that and gives you the actual force that it can withstand. So yeah, AG is your gross area of the column, FY is based on what type of steel, E is based on what type of steel, and K is that distance factor for between the zero moments on a column, and length is the unbraced length, and R is the radius of gyration. So yeah, we just plug all those in, and we get that this column can hold up to 853 kips, and that is unfactored. I'm pretty sure. Here we can see that in LRFD our factor is times 0.9, and for ASD you can do it times 1.67. Alright, so then next example is actually a beam. And so when you apply a load on a beam, sometimes it can cause the beam to buckle laterally and torsionally, so it will bend out and twist. And so assuming a W12 by 26 beam with a uniform load of 0.14 kips per foot and an unbraced length of 23 feet, what is the maximum allowable moment, and is it greater than the maximum moment caused by the load? So we go to F2, and we have all these values, and there's more values than I have screen. Okay. So yeah, we can plug in, this is our unbraced length here, and then all these values are in the tables at the, well, it says right here, in front of the AISC. So yeah, you can plug all those in and figure out what the maximum moment we can have is. So if we look here, our LB is actually greater than LR, so we're going to use our case C here and find our moment max is 111 kip feet. Yeah, feet. And if we go back here, we can see our WL squared is 0.14 times 23 squared divided by 8, and it ends up being greater, or not greater, the allowable is greater than the maximum moment caused. Okay. So finally we have a local buckling. So this is, and both these were full member buckling. This is an actual concentrated part of the member that buckles and causes the full member to buckle. So we have pictures of it right here. It's just a point where like an actual element of the member fails. So if the width over the thickness of an element of a member is between gamma P and gamma R, then that element is said to be compact. So if it is compact, then it won't have local buckling. However, if the width over thickness of a member is greater than gamma R, then the element is said to be slender. So table B 4.1b contains all the gamma values, and so you can compare those. But we're going to find what is the allowable moment for an HSS 12 by 3 by 5/16 for flange local buckling. So that's saying that we have a rectangular column, and part of that, or one of the sides of that, is going to be have local buckling. So we can go to, and this one's pretty simple. So we just have values again. Alright, so we can plug in our values here, and so yeah, here is where it says if it is compact and local buckling does not apply. For sections with non-compact flanges, then you'll use case B here, and if you have a section with a slender flange, then you'll use section C. Okay. So this was we had a slender flange here, and so our moment allowable is going to be 547, and yeah, we can design the column using that. Alright. So finally, I have some videos showing what the end conditions actually look like. So
you clicked it twice. It's too plain.
So this is the
Volume, if there's volume on the wall at each.
I don't think it's really sound. But yeah, this is has pins on both ends, and so if you remember, it just curves, and you can see it actually does that. So I thought it was pretty cool that it actually does look like the picture does. And it doesn't like break in half or anything, it just goes to the point where it will not elastically go back. fixed. So this one, instead of just curving out, it's going to start straight, and then it's going to go sharply, and then come back to being straight because it's fixed on both ends. So you can see that starting, and then this middle section will go out even further. But then when it gets back, it's straight. And then we have a fixed pin. This isn't actually a real one, but this is a simulation. And so it starts out straight and goes up to a strong bend and then comes back and doesn't go straight because the top is pinned. And then finally, we have a fixed free. So it's going to be straight at the bottom, and then the top is able to actually swing all the way out. And it would just keep going as you apply the load. What?
It's talking to the video.
Oh, okay. Yeah. All right. So any questions?